Thanks. All right, good afternoon, and thanks for having me. So today I'm going to talk about data engineering, data processing at Spotify, particularly with a Scala library that we built called Scio. And this seems like the only data engineering talk at Scala conferences. This Scala conference, or like usually there are fewer data engineering talks. On the plus side, we don't work with a lot of the complexity like side effects and like mutation states, but on the minus side, we do have work with a lot of the slightly unpleasant side of working with Scala, like Java dependencies, serialization, and GC. So those are some of the problems that we deal with. Anyway, let's move forward. Yeah, so a little bit about me. I've been at Spotify for 8 years since they launched in the US, and currently working with data infrastructure. And in the past, I've worked on music recommendations at Spotify as well. The team that built Discover Weekly and some of the features, if you use Spotify, you might have heard of. And before that, I worked at Yahoo Search, basically crunching web data with back in the Hadoop 0.20 days, so it was the early stage of Hadoop. And just a little bit mandatory stats about Spotify. We have a lot of users and a lot of music, and the users listen to a lot of music. And then we collect data and use that to provide information like recommendation and maybe reports and analytics to the creators, like artists and singers and bands. So we do use Scala a lot at Spotify, mostly for data engineering. We are on the Scala Center Advisory Board, and we're very grateful for a lot of the improvements they've done with the tooling ecosystem. And we do open source a lot, so most of them are GitHub, so check it out. Some use cases for data. I've already mentioned Discover Weekly, which is a weekly music recommendation playlist for you. Release radar, similar, but for like new tracks. A lot of these are actually very complex data pipelines. In the case of Discover Weekly, there are more than a couple dozen data pipelines running every week, crunching tens of hundreds of terabytes of data, and then produce recommendations for every single user. And there are like 100 million of them, so it's a lot of data crunching and fairly complex. So we have some scalability challenges, like the volume of data we are processing on a daily basis, the number of data sets. We have maybe like tens of thousands of data sets, and the number of engineers writing data pipelines. We have hundreds of them, and a lot of them are from a non-functional programming Scala background, a lot of them from Python or statistics or Java background, so they know very little about functional and Scala programming, and that was also a challenge to scale up. So as I said, those are some of the scalability challenges, but then there's also like a complexity from having so many pipelines, so many data sets, scheduling orchestration, all of these become pretty challenging. Testing data, be able to reason about the correctness of your code. And because we're a public company with a lot of large user base, like other complexities like encryption, user privacy, the data quality, these are all like the challenges we deal with on a daily basis. So a little bit overview of the history of data processing in Spotify. Spotify started as a Python shop, actually, around 10 years ago. And we started doing more machine learning data science work around 2011. We even built our own like orchestration and Python MapReduce framework called Luigi up there. It's a reference to Mario and Luigi because the world's two most famous plumbers. And we quickly learned that Python is not great for writing large-scale data pipelines. It's easy to write, but usually we don't write a lot of tests, and there's no types. It's hard to reason about whether my code will run correctly, and then the performance wasn't that great. So around 2013, we switched to Scala, and mainly to a scouting framework, which is open source by Twitter for running MapReduce jobs on Hadoop clusters. And our team, around the time, with like maybe 10 engineers, rewrote around 200 pipelines in a couple of months. It was pretty impressive, and the quality of the pipelines execution and performance was like hugely improved. We also tried a bit of other technology. We tried Spark a little bit for machine learning, and we were using Storm for real time, like ads targeting, recommendations. We also use Hive quite a lot, which is a SQL on Hadoop execution engine for doing ad hoc analysis. The problem is we have to manage all these different stack and different APIs and software. Also, there's a huge operational cost. I think at the time we had one of Europe's largest Hadoop cluster, more than 2,000 nodes. It's since been shut down, but it was not easy managing such a big Hadoop cluster. So moving on, a couple years ago, we started moving to Google Cloud and experimented with an open source project from Google called Apache Beam. And Apache Beam introduced this new idea called unified batch and streaming processing, and offers a couple of language SDKs. There's one for Java, Golang, and Python. And because we like Scala for data processing, so we built a Scala framework, Scio, on top of Apache Beam. And Apache Beam also has the idea of SDK separation between SDKs, which is the language you use to write pipelines, and the runners, which is the execution engine, which does the heavy lifting. And there are a couple of runners available, namely Dataflow, this one here, and there are ones for Spark and Flink and a couple of other popular data processing frameworks. Dataflow is a Google product, and then we run mainly on it. And it has a couple of components for like connecting with other Google storage services like BigQuery, Bigtable, TensorFlow, and Spanner. And we use most of these products in our day-to-day data processing. So about Scio, it's a Scala API for data processing. Obviously, the API is very similar to that of Scouting and Spark. So you can see here like a typical word count example with maybe 5, 10 lines of code. And the equivalent Java example will be 100 to 200 lines of boilerplate. So it's very attractive to data scientists and analysts who wants to get a job done relatively quickly. And it runs on a couple of different runners, as I said, and it's also open source. And we use it for both batch and streaming. Next. I imagine if I were to find some Latin speakers, this would be the place. And there's actually an interesting story behind the name. It's according to Google and Wikipedia, it's pronounced Scio, and it's Latin, which is a kind of Latin they speak in the church, apparently. Anyway, the story behind it was I was hacking on the Apache Beam API, and I was sitting next to this guy, one of our data scientists, research scientists. He's actually from Venice, not too far away from here, and he suggested the name, and it sounds just a very nice fit. It's a Scala library, and the name starts with SC, ends with IO, so we decided to pick that as a name for the framework. Moving on, so why do we like about Scio? Well, obviously it's Scala. It's a great fit for data processing because data processing is very functional in nature. You just read immutable collections of data applying pure function transformations. So it's easy to reason about correctness. Performance is also great. It's easy to write code that runs fast and correctly. So productivity is hugely boosted compared to people moving from a Python environment. Of course, there's type safety, which gives us extra guarantee that the code will work correctly. And we have a lot of people from other companies using these popular Scala frameworks like Scouting and Spark, and it's easy to onboard users because they're already familiar with the API. And we use a lot of Scala libraries for numerical computation like Breeze, which is a linear algebra and machine learning library, and also Twitter's LGBot for approximate parallel computation. We also use macros and shapelets pretty extensively, mostly for like manipulating data types, like transforming data, or code generation for like between JSON and BigQuery and other data types. So Scio at Spotify today, it's grown a lot over the last couple of years. I think when we started using Scio, there were maybe 20 people running Scala at Spotify, and today there are at least 300 users, and a lot of them are not Scala programmers. They're data scientists, as I said, data scientists, Java backend developers, and many of them probably don't even know what a Mona is, but they managed to write pipelines that works pretty well and pretty fast. And we have 400 unique production, more than 4,000 unique production jobs, and daily execution probably tens or like close to hundreds of thousands of jobs. So it's pretty impressive. So one of the biggest problem with data processing is actually serialization, no surprise. And one of the greatest improvements in the latest release 07 is a static coder, mainly contributed by Julian, who works with us. And there's a bunch of other improvements. We're gonna skip some of them, but let's dig into the coder implementation in detail. So before 07, we use a library called Scio for serialization. It's a Java library that does a lot of like bytecode manipulation, and it's completely runtime reflection based. So both speed and performance are not great. It has to do runtime reflection on the data type to figure out the best way to serialize objects. And also it writes a lot of additional metadata for each record being serialized, so speed and size penalty. And Scio is actually the serialization library used by most Scala and Java data processing frameworks. As far as I know, Spark, Storm, both use Scio, Flink and Scouting. Flink has a macro-based serialization, but also fallbacks to Scio. And we replaced that with a new compile time derived coder based on Magnolia. Basically, we have a case class called T, and we have some primitive implementations for example, like integers, strings, maps, lists. And then at compile time, we can derive any arbitrary user types like case class, Avro, or protobufs based on the existing coders and can compose them. And compile time, that makes coder much more type safe, much more performant, and we can reason about how and exactly what is being encoded. It also allows us to do a lot of the run optimization. For example, Bean design has some mechanism for type hinting, like whether a type T is safe to encode deterministically. For example, float is not a deterministic encoding, like IEEE floating point numbers, and it shouldn't be used as a key when you do your grouping, by, or joining operation. And we can detect that by using a static coder. And consistent with equals, a notorious example is array. Java arrays don't have a consistent equal method and shouldn't be used for equality comparison. And in that case, you have to serialize it as bytes. So a lot of these optimizations are only possible with Magnolia compile time derived coder. But we still keep the Scio as a fallback in cases Magnolia fail. So all of these are based on mainly Magnolia and a lot of macros to resolve coders at compile time. So it is a breaking change, and the only main change is really the signature. So before 07, we have this class tag, which is a Scala compile time reflection. And then after 07, we replace it with implicit coder and a macro, and Magnolia derives it at compile time. And we also had some Scala fixed rules to automate the migration, which works pretty well in most cases. The results. So one of our largest set of jobs is anonymization, because we have user private information, user data, anything that we collect from the user, every track play history, we have to encrypt them, and that's tens of terabytes of data every day and every hour. So it's pretty significant cost saving by using the new coder system. So we encrypt user data using unique key per user. So when the user decides to either leave the service or request data deletion, we can delete the key, and as a result, basically deleting all the user's data. So before the 07 upgrade, we were mainly using Avro generic record, which has a huge overhead because Avro's records can be serialized without a schema. So in that case, and Scio cannot figure out the proper schema at compile time. So instead, it writes the schema per record, which is it's a significant overhead. And after 07, we have implicits to override the Avro generic coder at compile time, and also able to throw a warning when such implicit is missing. So basically, to warn users to stop using the inefficient types. And this achieved 60% cost saving in one of our largest jobs. And also pretty significant time saving as well. Yeah. Let's see. Oh. So basically, the TLDR is serialization, especially serializing data through disk or network is usually the biggest bottleneck in the data processing job, so do not overlook that. And we do have a lot of other overheads, like in some cases, user might write inefficient code that does a lot of copying, like the Scala collection, the overhead of copying data. But in most of those cases, much less problematic than data serialization through the disk and network. Another improvement that's in progress right now is join. So as I said, Scio already has a lot of built-in syntactic sugars provided compared to the native Beam, Apache Beam SDK. For example, we have a lot of special cases of joining, like very large site joining a smaller site usually like within a couple hundred megabytes that can fit in memory. So in those cases, you can do a hash join by copying the smaller site to all the workers. And in MapReduce terminology, this is known as a map site join. And there's also like the large to medium join. In that case, we use a blown filter to split the large site so that only the keys that overlap with the smaller site goes through a shuffle, and the rest stays on disk. And then there's a more extreme case, large join. And in one case, we actually have a job. It's one of the larger data flow jobs that shuffles 150 terabytes of data every day. And it's a pretty expensive job. And we're working on improving it using a technology or a technique called SMB, or sort merge bucket join, which is an idea from relational database design. So the idea is basically to store every data set as buckets of grouped and sorted keys. So each bucket contains a subset of the keys which are already sorted, and which look like this. So you have an input data set, like a bunch of keys, and then I hash the key mod by the number of buckets and store them in separate files. And within each file, all the keys are sorted. So if I'm reading multiple data sets stored in the same format with the same key, instead of sending everything through network like a huge multi-terabyte shuffle, I can just read matching buckets of the files of the same bucket on the same worker, and then do an in-memory sort merge sort. In that case, I'm essentially doing the join without shuffling the data. And in practice, this has improved some typical jobs by at least 60%, again, cost and time saving. So the idea is basically at data producer side, we shuffle once by storing data in the sort merge bucket format, and then join everywhere without going through the shuffle. And there's a PR in progress. And there's some additional benefits. For example, because all the keys are sorted, compression works better in that case, so the files are actually smaller. We have the typical use case, as I said, the previous anonymization job. Every consumer of pretty much every core Spotify data set needs to join with the user decryption key to decrypt data and then to do any type of processing. So that would be a huge cost saving. We also have like a lot of machine learning features. For example, we have like different teams producing attributes of a track, whether the track is the tempo, the key, what kind of language, all these different metadata. They can be scattered across 10, 15, 20 data sets of tens, hundreds of gigabytes each, and avoiding joins in those cases, it's a huge performance improvement. The next big improvement in the upcoming 0.8 release is ease of use. In that case, particular case of Beam Scio. So Apache Beam introduced a new way to write pipelines. Previously, I had, like, as I said, language SDKs, like you can write code in Java, or in our case, Scala on top of Java. You can write in Go and Python, but they're introducing a new way, which is using Apache Calcite, a SQL engine, to analyze SQL query and then translate it into Beam code. In Scio 0.8, we're introducing some integration with Beam Scio, like coders for the Beam schema type, and Beam also has a row type as an intermediate representation of the data. So any type of data, like Avro, case class, Java, Projo, whatever, as long as you provide a conversion mechanism, we can represent it as like a relation table in Scio with a schema and a row type. So this is a classic, typical example of integrating Scala and Scio. So we can have S collection, which is the data type of parallel. It's similar to RDD in Spark, so it's like a parallel and distributed data set. In this case, it's an S collection of, say, a case class user. You read it from somewhere, we do some Scala code processing, and then you can apply a Scio, a seamless transformation, selecting from the collection with some Scio query, and then converting it back to a Scala tuple. So there are some questions that need to be asked because Scio query doesn't have any types, right? It's basically a stringly typed. It's a string essentially. So the questions are like, is this string a valid Scio? Is it the correct syntax? Are these fields, do these fields exist in the original input collection? What are the types, and can they be converted to the output that I expect? The answer is yes, because we already know the Scio query. We have an analytic engine calcite for parsing the query. We also know the input type at compile time because of Magnolia and all the Scala runtime compile time reflection. So you can replace it with a T Scio, the type Scio interpolator, and then this enables us to do compile time type checking. For example, this case, can you spot a bug here or error? There's a typo. Yeah, so yeah, it turns out phone is not a Scio keyword, so it reports that, unexpected. So these things we can handle at compile time. Another example, select name instead of username. Now we get a report that column is not available from the source data set. And the columns are defined by the implicit conversion between my type case class user and the Scio table schema. Another example of converting the output to a tuple of int and strings instead of string to a list of strings. In this case, I get another schema error that's incompatible because the first field, the username field, should be a string, not integer. And of course, there's an implicit conversion between any of these supported types to the Beam Scio schema and row type, so that we can use that as an intermediate and then have seamless automatic conversion between any data types. So that opens a lot of new possibilities for data processing, because today, even though we have a very nice API Scala for writing data processing code, there are still cases where it makes more sense to write Scio. For example, we can have programmatic code generation or templated code, and we can leverage that and mix and match, use the best from both worlds, either typed safe Scala code or a more flexible Scio code in the same code base. And of course, type conversion does extra checks like schema compatibility and whatnot. And one last point, as I said, we have a lot of users, a lot of pipelines. We probably have more than 1,000 pipeline repos, and managing them has been a pain historically, but in the last couple of months, we switched everything. We're switching everything to internal ecosystem monorepo, which is a unique versioning. So instead of everyone copy and paste the same SBT template and then write their arbitrary rules, we're consolidating them with this plugin and then using Scala steward. We have an internal Scala steward for auto-bumping plugins. So every time the infra team releases a new version of Scio or some bug fixes, it automatically pushes it to everyone, and everyone gets it for free. So, and that's it. That's all I have today. So, any questions?
Hello, thank you for the presentation. So I have one question. I usually work with Apache Spark, and so I saw that the API of Beam and Scio over Beam is quite similar. But one question is, do you find anything that you might miss using Apache Beam instead of Spark without this layer on top? And if you're using Spark as an execution engine, if you have found any difference between using directly Spark or Scio or Beam, and what are the cons for you of using this kind of abstraction instead of using the engine itself?
Okay, a couple of different questions, I guess. The first is rephrasing it, what's in Spark that's missing from Beam. So Beam is abstraction. It tries to abstract across multiple different runners. So in this case, like Spark, Flink, and Dataflow, and a couple more. And there are certain things that's unique to each runner that's not covered. Like the Spark case, the one I can think of is RDD can be cached in memory in Spark, but not in Beam. So Beam doesn't have a notion of in-memory caching. So if you're doing like interactive machine learning, Spark might be a good fit. On the other hand, I think it's Beam's design philosophy that caching should be implementation detail and not a user, a API exposed to the user. And in our real life experience, caching only works to a certain point, and then you hit JVM problem like GC and running out of memory, all sorts of issues. So it depends on your use case. So that's the first question. And the second one is, can you repeat the second question?
Okay. So if you are, first is what's the engine you actually use in production? And if you use Spark, if you have found any big difference in using it directly or through Apache Beam?
Yeah, so as I said, yes. So we use Dataflow as an engine because it's a Google managed service, which means we don't manage our cluster, and it's a lot less operational overhead. Spark kind of have a reputation for being hard to tune. There's a lot of parameters and different ways of operation, like there's Yarn and Mesos, and even today like Kubernetes, set up for running a Spark cluster. There's actually on the Beam website there's a compatibility matrix which shows the support level of each runner. For example, Beam is actually the first engine that introduced the unified batch and streaming API. And if you look at the Spark implementation, the Spark streaming part is actually micro batching. So it's doing like micro RDDs, and there's also the new structural streaming, but I'm not super familiar with that. The closest parity with the Beam Hyper model is Dataflow and Flink runner. Flink is pretty much modeled after the Beam or the Dataflow paper. So that's the first question. Second is are there anything missing from using Scio or Beam on top of the runners? The answer is yes, because it has to abstract away. So Beam has its own coder, in this case, the one I talked about. We used to use the cryo overloading for the coder, and now we have our own implicit compile time coder derivation. And this is actually superior than the cryo coder used by Spark and Scouting. But if you're using Flink, for example, Flink has its own type information macro for compile time coder derivation, which should work just as well. I don't have a lot of operational experience with Flink, so I can speak to that. But it's one of the things you lose. The other things you might lose is the add-on ecosystem. For example, Spark has an execution like the core, and it has like ML or a lot of IOs for other components, and what else? Like Spark SQL. Those things, those add-ons are not covered by Beam, the Beam abstraction. If you look at the Beam API, the core API is super simple. It has only two operations: apply, which you can apply any kind of parallel operation, like Pardue, like map, flat map filter. Those are Pardues. And the other is group by key. So any join, shuffle, count by key, count by value, those are grouping operations. So everything is implemented with one of these two. And everything else is extra ecosystem built on top.
Thank you.
Any other question?
Thank you. Hi. Just to know, which version on data flow are you supporting with Scio right now? And in general, how long it requires to support the latest version of data flow runner?
We try to stay pretty current. The latest Scio 07 runs on like Dataflow or Apache Beam 2.10, I believe. The latest beta 0.80, beta 1, or beta 2 actually. No, beta 2 is not released. Beta 2 is about to be released. That will be on Beam 2.16, which is being released as we speak. So we try to stay on the latest. That's the Beam version, and Beam is the SDK. So Beam might run on some version of Spark or Flink or Dataflow. And in the Dataflow case, it's a Google proprietary system, so there's actually no public versioning info.
Questions? No questions. Thank you, Neville.
Thanks.